Hi everyone, I'm going to go over the data analysis portion of the Streamlab. We'll discuss a little bit more about the rank abundance curves and the Simpson's D, but just briefly, as I've already recorded a video going over this more in depth, mainly we will focus on the t-test. So at least for my lab and some of the others, we will be adding our calculated averages from this year's lab to an index of long-term data from previous semesters' data. So this might be different for your TA. Make sure to check in with them. But for my section, so Kelsey's section at least, we will be calculating the average temp, DO, Simpson's D, and discharge for the Rivanna and the Steger for this year, quote, as if we got to sample it, and we will be adding it to a data set of previous semesters' averages for these sections to run our t-tests. So I will be posting that up to Colab, the previous year's data, and if this does not pertain to you, then feel free to ignore it. Anyway, the reason that I'm doing this is that having a larger sample size lends itself to a more robust data set and more robust statistics. So instead of running stats on just the average for Steger for 1 year versus the average for Rivanna for the same year, essentially using 2 data points, or if you use all of your raw data, we would have 3 to 4 for each river, right? It's not the most robust sample size. So in our case, we are looking at the data in terms of the year. So fall 2020, had we been able to sample versus the average of the mean for DO, temp, Simpson's D, and discharge for the past 10 or so years. And this is set up in that we have data from the previous semesters and we're treating them like they're a year. So we can kind of pretend we're creating this longer term data set. And that way we can look at the RCC as it pertains to this year or this time in particular that we sampled, as well as the overall average or a multi-year average between the streams, and see if the RCC matches our 2020 data and if it matches or pertains to our multi-year data. So again, check with your TA, and if this does not pertain to you, then don't worry about it. So again, what is Simpson's D? It's a calculated diversity index. It varies from 1 to 0, 1 being maximum diversity. All individuals sampled are from different taxa, versus 0, where there's no diversity. All individuals sampled are from a single taxa. So obviously, the greater the number, the greater the diversity, the higher the Simpson's D index is. Again, it's calculated by looking at the proportion of individuals that make up a taxa versus the total population size and the total number of taxa represented per population. And we would calculate Simpson's D for Rivanna and Steger. So you end up with 1 value for Steger and 1 value for Rivanna. And you can look all of this over again in my previous lecture that I recorded. It will walk you through the dinosaur example and you will calculate these more in depth. So I'm going to skip over the dominance diversity curves, which is essentially just visualizing how rich and even a community is. So again, the function of the length of the curve, as you can see there, Steger's curve is much longer. It goes from 1 to 10. And a function of the steepness of the curve, you can see here the Rivanna has a much steeper curve, that line there in pink. It tells you how rich or even a community is. If a community is very rich, it has a longer curve, which means more taxa are represented. There are more taxa present. And then the evenness of the community refers to how many individuals make up each taxa. How highly dominated is a system by 1 to 2 to 3 taxa versus a more even spread of individuals across more taxa, say maybe 1 to 5 taxa. And again, you can revisit the dinosaur example, which talks about this much more in depth, but it's important to note in terms of diversity, whereas Simpson's D simply gives you a number, the rank abundance curve or dominance diversity curves show you what that population looks like in terms of richness and evenness. And this also plays into diversity when discussing the health and the indication of the 2 streams for how healthy they are. So For the abiotic data, we will be testing the differences in means, so the differences in the averages for dissolved oxygen, temperature, and discharge, and also Simpson's D, so the D values that we calculated. And we want to know, are these means, are they significantly different? So the RCC states that streams of different orders should have significantly different abiotic features. So in terms of dissolved oxygen, temp, discharge, and then Simpson's D is what we're lumping in here as well. And also, how are they different? So the RCC will make predictions on whether the lower order stream has colder temperatures or greater or less dissolved oxygen compared to the higher order stream. So we are testing, one, are they statistically significantly different at all? And then two, are they different in the way that the RCC predicts? If you have already forgotten this, check your pre-reading for Streamlab in the manual and look at my previous lecture that outlines the major characteristics of high order versus low order streams, just to refresh what the RCC is predicting, so you can determine whether you expect Steger to have lower or greater discharge than Ravana, more or less dissolved oxygen compared to Ravana, more or less diversity compared to Ravana, and then temperature compared to Ravana. So the overarching RCC prediction, again, is that they are statistically different between high versus low order streams, and that they are different in a certain way. So we are testing this using a t-test. Now, again, if you aren't using the multi-year data, you'll be running your t-tests on all of your raw data. So your 3 to 4 samples for discharge, for dissolved oxygen, for temperature, etc. Versus my section, some other sections, you will be adding your averages to the long-term data sets, and you'll be running a t-test on that. Okay. So to determine whether they're statistically different, we are going to treat our samples as populations. So t-test tests the difference in means between populations, and this terminology can lead you to think that they're talking about animals or organisms, but it can be any data set. So in our case, our populations are our dissolved oxygen data set from Steger and our dissolved oxygen data set from Ravana. Those are being treated as our two populations. So obviously the null hypothesis is that there is no effect or that there is no statistical difference in the DO between Steger versus Ravana. An alternative hypothesis, or what the RCC predicts, is that there will be a difference between the two, a significant difference in the DO between the Steger and the Ravana. Now, these don't need to be stated. Null and alternative hypotheses are given and are understood. You should just be talking about the data as to whether or not they validate or support the RCC, and whether or not they support or refute your more personal hypothesis based on a more honed in selection of some of these variables that we are measuring. So the assumptions of the t-test are that the populations are sampled independently at random, and that the variable being sampled is normally distributed in each population. You'll have a bell curve sample, not skewed. So we're expecting to have a normal distribution, sampling at random, of course, to try and make it as fair and even between the two and avoid experimental bias or surveyor bias. So the t-test studies the difference between group means and the variability of groups. In order to figure out whether your mean is actually real and statistically different, you need to look at the variability within your population, or in this case, our data set. Let's just say for dissolved oxygen in Steger versus Ravana, and look at the variability within those data sets, and then look at the variance between the two means. So it is looking for signal versus noise. The signal is the actual difference between the two means, or your averages. So let's say this is DO for Steger and this is DO for Ravana. And we are looking for the difference between these two means to see, one, are they statistically significantly different? And then, is that true? Can we believe that? And then the noise is the variability within your population or within your data set. So it's the range of data you have for DO for Ravana versus Steger. So we're trying to figure out, are the means actually different, or is there such variability within the population that it muddles the difference between these means and that the means we see aren't actually true? So more variable groups, or having more variability within a group, offers less certainty about where the mean actually is. And then the bigger the difference is between the means, meaning the less variability you have in your population or your sample size, the more certain you are that the difference between the means is true. And you can see that better here. When you have nice, concise data, and here's the mean, you'll see that it all sort of converges on this nice average, and you don't have a lot of variability. You can say this might be -2 to +2, right? So you just have this spread. Versus if you have a lot of variability, and this is the mean, you have some outliers that are much higher, some outliers that are much lower, and maybe this is, you know, -10 over here, and this is +10 over here. So you have a much larger spread of data. So the more your data looks like this, nice and concise, the more accurate the difference between your means may be, or the more certain. If it's more spread out like this, then you have a lot of variability within your population or your data set, and the difference between means is not as certain. You can see that here, right? Over here, we have low variability between your two populations. You have very distinct, clear means. When you have medium variability, you can see that there's some overlap happening here, right? So your outliers are starting to mesh and blend. There's not actually as much nice, clean space between your two means. And then when you have high variability, you have a ton of overlap. Look at all of this data overlapping. So even though you have a mean here and a mean here, let's say a mean for Steger's DO and a mean for Ravana's DO, with all of this variability and this overlap and these outliers, how can you tell that this mean is actually statistically significantly different from this mean? So that's what the t-test tests. It tests the difference between means in relation to the variability within each population. And that will tell you whether or not you actually have a difference between means, whether or not there's actually a difference in the dissolved oxygen for Steger versus the dissolved oxygen for Ravana, and whether or not you can trust that. We went over this a little bit for our forest lab, but essentially all of these stats are performed in order to determine whether the data we are seeing can be trusted or not. We have various types of errors where we reject or accept hypotheses that are actually false or actually true. And these types of errors is what we try to avoid by using a significance value or a confidence value. So if you remember from Forest Lab, our alpha is the significance level of the test, and it is the probability that the null was rejected properly. So you reject the null when it is indeed false, right? And it means there's data to support your hypothesis or that something is going on. And this is represented by our p-value. So we have a probability or a confidence level of 0.05, and that means we are allowing a 5% chance that we might be making a type 1 or type 2 error where we accept or reject hypotheses that are actually false or true. So accepting the hypotheses incorrectly per se. And we are 95% confident that our data is correct. So the trends we're seeing is correct, the difference in means we're seeing is correct. And that is why we set the p to 0.05, and we need it to be less than that, right? So to be considered statistically significant, we want a p that is less than 0.05. And that gives us a 5% chance to be wrong, but a 95% chance that what we're seeing is real. Now, these are all pre-populated in your Excel. Most significant tests run based on this. You might see this change in different types of studies, but the typical set is 0.05. So 5% chance that you're wrong, 95% chance that the trends or differences in means you're seeing are actually true. So when we perform our t-test, we are doing a two-tailed t-test. Sometimes this is called two-sample. So it's a two-tail or a two-sample t-test. This means that we are not concerned with directionality. So a t-test can tell you whether one population is significantly larger than another. It can also tell you if one population is significantly smaller than another, or it can just tell you that they're significantly different. And that's what we're aiming for. We're not, concerned about whether one is larger than the other specifically or smaller than the other specifically. We just want to know, are they different? So when we refer to directionality, we mean it can be smaller or it can be larger. So that's why we have a two-tailed or two-sample t-test. And then we assume unequal variance. So in a natural system, you are going to have differing spreads of variance within your sample sizes. So let's say maybe for the DO and Steger, we get a variance something like this, very little variance. And then for the Ravana, we might get a much larger variance. Let's say this is for temperature. And Steger is small and cold, whereas Ravana is large, possibly stratified. So it might have some very warm pools and some very cold riffles, and therefore have a much larger variance in its population, or as we're using them as the data set, right? So we have to assume unequal variance. We don't know, there's no way to know yet, that the spread or range of data for Steger is going to match that of the Ravana. So we do a two-tailed or two-sample t-test assuming unequal variance. And make sure you pick this correctly when you put it into your data analysis tool pack or your solver pack, so that it will give you the correct t-test. Now again, for my class and some others, we will be calculating the average DO, Simpson's D, discharge, and temperature for Steger and Ravana for this year, quote unquote, and we'll be adding it to the previous year's data, and we will be running a t-test on that whole data set. Now, for some others, you will be running a t-test on your raw data between the two streams. So make sure you check with your TA and listen specifically to their instructions as to which one they want. The things you'll be reporting are the mean value of the variable for each stream. So the t-test will give you the overall average. So in the case of my students, which will be doing the long-term data, it will give you the overall average of an abiotic feature for the last 10 or so years. And then you want the two-tailed p-value. So it will spit out other p-values, but you want to make sure you choose the two-tailed p-value because we are running a two-tailed t-test. Now keep in mind the hypotheses following the RCC when you're running these tests, that one, again, they should be statistically different between high and low order streams, and then how they should be different. So which stream should be colder, which one should be warmer, which one should have more or less DO, which one should have greater or less macroinvertebrate diversity, etc. And keep that in mind. I will be walking you through how to do t-tests both on the long-term data and then for those of you not using the long-term data on just your raw data from the year 2020, and that will be in the next video I post. Now remember, you should be thinking about the big hypothesis, which is how accurate the RCC is, how useful it is, and then your more personal hypothesis. So looking at the specific abiotic and biotic variables that we are measuring in this lab and focusing on whether or not those relationships or difference in means you are actually seeing.